Let's take a look at a binary number. For those of you that speak binary, 00011001, which of course you all know what that meant, right? Now, Brian and I were just talking about how binary is simply an on or off switch. When I take this binary number and I append it to that box that we had in the previous slide, you can see that 16, 8, and 1 are all on, and everything else is off. So when I flip to the next slide, you'll see that 16, on this very bottom line, we have 16, 8, and 1. All the other numbers are turned off, so they don't pass through. So everything that is turned on will pass through and be added to get to the decimal that this represents. So 16 plus 8 plus 1, this binary number is 25. This is 4-bit binary, which you all know now is a nibble. This isn't a byte, this is half a byte, which is a nibble. We're counting from 0 to 15. Now, we're not going to go over this slide. You can pause it and review it at your leisure. But this is counting from binary from 0 to 15. It's a fun exercise. Do this on a piece of paper. You'll have a blast. Here is the opposite, Brian. Let's take a number and let's convert that into binary.
Awesome.
Yes. Now, this is a basic modulus operation. Now, we're not going to use modulus in this example because some people may not know what that is, but I think if you've gotten this far, you should know what division is. And you should know what a remainder is. Mm-hmm. And that's really all that we're trying to get across here. So let's take this number 21, Brian. Now, let's take 21 and divide it by 2. What happens?
We get 10.5.
10.5?
So we have a remainder.
We have a remainder because we have a 0.5.
Right.
So what does that mean, Brian?
That means we have a binary bit.
We have an on bit. Woohoo!
So don't think too much about why we're doing this. This is a shortcut technique for converting integer to binary.
Exactly.
So bear with us and you'll understand.
Now the next number is 10. Now where do we get 10? Well, 10 is the whole number of 10.5. So whatever the division is in the previous step, we drop the remainder and take the whole number. So now we perform this exact same operation with the number 10. So 10 divided by 2 divides evenly. So there is no remainder.
Right, just 5.
So now what happens, Brian?
So now we have no binary bit.
Oh, man, I thought this was getting fun.
And then the 5 carries down to the next current number.
Now what happens?
But now we divide it again. Now we have 2.5.
Oh, goodness.
Since we have a remainder, the remainder goes over to the binary bit is on, and we drop the 2 down.
Oh, goodness. Now this divides evenly.
Yep.
So
no
it's
binary
0.
bit. Drop the 1 down. 1 divided by 2. We have a half. There's a remainder.
Yep, so that's on. Now, here's the key. Once we get to 0, meaning when we do our division and the value is 0, we're done. I mean, technically not. You could go 0 to infinity because these numbers don't count, but practically you're done at this point. Here's our number in binary. Here's 21 in binary.
Just like everything else, we're kind of writing it backwards from what would be intuitive. So we write it from right to left as we go top down.
Yeah, so once we get this bit value, we have from top to bottom, we have 101010. We actually read that from bottom up to get the binary value.
Right.
So it's going to be 010101. Now, how can we prove, Brian, that this is actually 21 in binary?
Well, let's put it back on our chart to convert it back to a decimal number.
That is a spectacular idea.
So based on this number, we have the on position in the 0 position, the 2 position, the 4 position, and everything else is off.
So 16, 17, 18, 19, 20, 21. We have successfully converted 21 to binary and back to a decimal. Here's just another example. We're not going to spend too much time on this, but here's taking 47, converting that to a binary number, and converting it back. So this is just another example of converting a number from a decimal to binary, from a binary back to a decimal.